electromagnetism, and fluid dynamics. Even the simplest questions near a black hole become complex. Consider the path of light. Near a black hole, gravity bends light in dramatic ways. Some photons circle the black hole multiple times before escaping. Others are pulled in and never return. To a distant observer, this bending creates a shadow surrounded by a glowing ring. This ring is what we saw in the first image of a black hole. It is not the event horizon itself, but the region where light is trapped in tight orbits. The image provides direct visual evidence of the intense spacetime curvature predicted by general relativity. The event horizon remains a boundary that cannot be crossed from the outside, but can be crossed from within, moving forward only in one direction. Once an object passes through the event horizon, it cannot turn back. It is drawn inevitably toward the singularity, where spacetime collapses into infinite density. From the perspective of the falling object, this journey continues smoothly. However, from the perspective of the outside universe, the object appears to freeze at the horizon, fading slowly as its light becomes redder due to gravitational effects. This difference in perspectives is a hallmark of relativity and demonstrates the separation between external and internal realities near a black hole. Time itself behaves differently near a black hole. An object moving near the event horizon experiences time more slowly compared to distant observers. If a spacecraft were to orbit a black hole at close range, the crew would age more slowly than people back on Earth. This form of time dilation has been confirmed experimentally using satellites and clocks, but black holes amplify the effect dramatically. In theory, one could travel close to a black hole and return to find that far more time has passed in the rest of the universe. This concept has inspired countless stories, but also remains an important aspect of real physics. Black holes also affect space in ways that are difficult to imagine. The warping of spacetime near the event horizon alters the shape of the surrounding region. Space becomes stretched in one direction and compressed in another. Any object approaching the black hole is subjected to tidal forces. These forces arise because gravity acts differently on parts of the object that are closer or farther from a singularity. If the black hole is small, these forces can tear objects apart long before they reach the horizon. If the black hole is very large, the tidal forces at the horizon may be mild, allowing objects to cross the boundary without immediate destruction. This difference makes supermassive black holes surprisingly gentle at their event horizons. Despite their mysterious and often terrifying reputation, black holes obey the laws of physics. They are not gateways to other universes or cosmic monsters that swallow everything in sight. They are simply objects with extremely strong gravity, behaving exactly as the equations of general relativity predict. They do not actively pull everything toward them. Instead, they influence their surroundings based on distance and mass. If our sun were replaced by a black hole of equal mass, Earth would continue orbiting normally, although the planet would experience perpetual darkness and cold. Black holes can even coexist peacefully with entire planetary systems. If a star collapses into a black hole without disrupting its planets, those planets could continue orbiting the black hole indefinitely. These hypothetical systems could contain worlds forever shrouded in darkness, illuminated only by faint radiation from the surrounding environment. While such planets would not support life as we know it, their existence would demonstrate the versatility of gravity's influence. The behavior of matter near a black hole offers clues about the internal physics of these objects. Scientists study X-rays, gamma rays, and radio waves emitted from accretion disks to understand temperatures and motion. Observations reveal swirling patterns of hot gas containing charged particles moving at nearly the speed of light. Magnetic fields shape the motion of the gas and generate jets that extend thousands of light years. These jets may play essential roles in distributing energy and matter across galaxies. The study of black holes also intersects with quantum physics. According to quantum field theory, empty space is not truly empty. It contains virtual particles that constantly appear and disappear. Near the event horizon, these virtual particles can separate, with one falling into the black hole while the other escapes. The escaping particle becomes real radiation known as Hawking radiation. This radiation causes the black hole to lose mass over time. The process is incredibly slow for large black holes, but for small ones, it becomes significant. If a black hole loses more mass than it gains, it will eventually evaporate completely. As it shrinks, its temperature rises and it emits more radiation. Near the end of its life, it would release a burst of energy before vanishing entirely. This final burst remains theoretical because no such event has yet been observed. Nevertheless, it suggests that black holes have finite lifespans and play roles in both the creation and removal of matter from the universe. The existence of Hawking radiation also deepens the information paradox. If information cannot be destroyed, how does a black hole preserve the information of everything it has consumed? Does the information escape in the radiation, or is it somehow encoded on the event horizon itself? Some theories propose that the event horizon acts as a two-dimensional surface, storing information in a holographic form. This idea, known as the holographic principle, suggests that the universe itself may be fundamentally two-dimensional with three-dimensional space emerging from deeper physics. The search for a solution to the information paradox has driven major developments in theoretical physics. It has inspired new models of quantum gravity which attempt to unify gravity with quantum mechanics. String theory, loop quantum gravity, and other frameworks offer potential insights, but no complete answer has emerged. Black holes thus remain central to understanding the fundamental nature of reality. Black holes also challenge our understanding of singularities. A singularity is a point where density becomes infinite and known laws of physics break down. Singularities represent limits of our understanding rather than literal points of infinite density. Many physicists believe that quantum effects will smooth out the singularity, creating a new form of matter or energy. Some theories propose that the core of a black hole may contain exotic quantum states or even a dense region without infinite density. But without direct observation, these remain hypotheses. As research advances, new discoveries continue to refine our understanding of black holes. The Event Horizon Telescope is being upgraded to capture sharper images, including movies of accretion disks in motion. Future gravitational wave observatories will detect mergers from farther distances and lower frequencies. Space telescopes will study jets and disks in greater detail. Each new observation brings us closer to unraveling the mysteries of how black holes are born, evolve, and eventually disappear. Black holes are not just astronomical objects. They represent the meeting point of cosmic evolution, physics, and philosophy. They raise questions about the nature of time, the structure of space, and the fate of information. They reveal the power of gravity, yet also highlight the limits of human understanding. They are windows into realms where intuition fails and mathematics becomes the only guide. Despite their complexity, the underlying story of black holes is simple. They are born from matter collapsing under its own gravity. They grow by consuming material. They interact with their surroundings, and they eventually fade away. Their entire existence is a testament to the power of the natural laws that govern the cosmos. The birth of a black hole is not only a violent event, but also a deeply transformative one. A star that has lived for millions or billions of years suddenly reaches its final moment. Its core collapses, its outer layers erupt or fall inward, and in the span of seconds a new object is formed that will outlive the star by an unimaginable amount of time. This transformation marks a shift from a life shaped by nuclear reactions to an existence governed solely by gravity. When a massive star exhausts its nuclear fuel, it can no longer resist the inward pull of gravity. The outer layers may still hold shape, but the core becomes unstable. The pressure that once supported the star fades as nuclear fusion stops. Gravity pushes inward faster than the star can respond. The core contracts, heating up as it shrinks. At first, electrons are squeezed into protons, forming neutrons. If the mass is low enough, the collapse stops and a neutron star is born. But if the mass is too great, nothing stops the collapse. The core shrinks further, compressing matter to extreme densities until the event horizon forms. The formation of the event horizon marks the creation of the black hole. The horizon is the boundary within which gravity is so strong that not even light can escape. Beyond this point, all physical meaning becomes unclear. The collapse continues into regions of spacetime that no external observer can ever witness. The star's identity disappears, replaced by a region of space with intense curvature and a singularity at its heart. The outward explosion of the supernova may enrich surrounding space with heavy elements, but the core is forever lost behind the horizon. Many stars end their lives quietly without dramatic explosions. In some cases, the collapse is so rapid and complete that the star implodes silently. This is known as a direct collapse. The star simply shrinks into a black hole without producing a visible supernova. For astronomers, this event is hard to detect because there is little light or energy released. The only clue may come from the disappearance of the star or from subtle changes in the motion of surrounding objects. Direct collapse is believed to be responsible for the formation of some of the most massive stellar black holes. When a star undergoes direct collapse, a larger portion of its mass falls inward rather than being ejected. This contributes to black holes with dozens of solar masses, or even more. Observations of gravitational waves from merging black holes suggest that these heavy stellar black holes are more common than previously expected. As soon as a black hole is born, it begins interacting with its environment. If it forms in a binary system, the gravitational balance shifts abruptly. The companion star may be thrown into a new orbit or may spiral closer, depending on the dynamics. In some cases, the black hole may begin pulling material from the companion. This can lead to persistent X-ray emissions that reveal its presence. Over millions of years, the black hole may consume large portions of the companion star, leaving behind a white dwarf or stripping it entirely. In dense star clusters, black holes may form frequently. These clusters contain thousands or millions of stars packed closely together. As the stars reach the end of their lives, some collapse into neutron stars and black holes. Interactions within the cluster cause heavier objects to sink toward the center. Black holes therefore migrate inward, forming a dense core. In this core, black holes may interact, merge, and grow. Over long periods, one black hole may dominate the cluster, consuming or merging with others. This process could give rise to intermediate mass black holes, which are otherwise rare. Understanding the dynamics of star clusters provides insight into the emergent behavior of black holes in crowded environments. These environments are violent and chaotic. Stars pass close to one another, changing their orbits. Black holes encounter stars and disrupt them, sending them out of the cluster or pulling them inward. The cluster may lose mass as stars are ejected. Eventually, the cluster may dissolve entirely, leaving behind a few surviving stars and a massive black hole drifting through the galaxy. Galaxies also contain environments where black holes can grow rapidly. In the early universe, the density of gas was higher, allowing black holes to feed more easily. When gas clouds collapse under their own gravity, they can form stars, but they can also funnel material towards central black holes. Jets from the black hole can blow gas outward, regulating the growth of new stars. This interplay between feeding and feedback shapes the structure of galaxies. As galaxies grow, they often collide with one another. Galactic collisions are common on cosmic timescales. When two galaxies merge, their stars mostly pass by one another because space between stars is vast. But their gas clouds collide, compressing and triggering bursts of star formation. Their central black holes are drawn together by gravity. Eventually, these black holes merge, forming a more massive one. Such mergers produce gravitational waves that ripple across the universe. Over billions of years, galaxies grow larger through repeated mergers. The supermassive black holes at their centers grow as well. They consume gas stars and other black holes. Each merger contributes to the black hole's spin and mass. The direction of spin may change depending on the direction of incoming material. This creates a complex history recorded in the rotation of the final black hole. The center of a galaxy can be chaotic. Stars orbit at high speeds, influenced by the gravitational pull of the central black hole. Gas clouds travel in turbulent flows. In some galaxies, rings of young stars form around the black hole. In others, the black hole remains hidden behind dense clouds. The Milky Way's black hole sits in such a crowded region. Dozens of stars orbit within a few light hours of it. Their movements create a dance choreographed by gravity alone. Observations of these stars allow astronomers to calculate the mass of the black hole with great accuracy. This technique provided some of the strongest evidence for the existence of supermassive black holes. The stars follow elliptical orbits similar to planets, but on a much smaller scale. Their speeds sometimes exceed thousands of kilometers per second. Their paths curve sharply as they pass near the invisible center. The existence of these fast-moving stars shows that the central object cannot be a cluster of smaller objects. A cluster would scatter and dissolve over time. Only a single dense object with immense gravity can account for the observations. This conclusion reinforces the idea that supermassive black holes sit at the hearts of most large galaxies, including our own. Black holes can remain calm for long stretches of time, but their hunger can awaken suddenly. If a gas cloud falls toward the black hole, the inner region becomes active. The accretion disk brightens. Jets erupt. Radiation floods outward. This activity may last briefly or may continue for millions of years. When the material is consumed, the region becomes quiet again. The cycle repeats depending on the availability of fuel. The feeding process is extraordinarily efficient. A black hole can convert a significant portion of the infalling mass into energy. This makes black holes some of the brightest objects in the universe, despite the fact that the black hole itself emits no light. The glow comes not from the black hole, but from a material around it. As black holes grow, they influence larger scales of cosmic structure. Their energy can push gas away from galaxy centers. When gas is pushed out, it may collect at greater distances, forming rings or shells. These structures may later collapse, forming new stars. In this way, black holes indirectly help distribute material across galaxies. The influence of black holes extends even to intergalactic space. Jets from supermassive black holes can reach far beyond the boundaries of galaxies. They carry energy and magnetic fields into the surrounding void. These jets can heat intergalactic gas and shape the large-scale structure of galaxy clusters. In some cases, jets carve enormous cavities in the gas, filling galaxy clusters, creating bubbles tens of thousands of light years wide. These bubbles serve as records of past activity. By studying them, astronomers can reconstruct the history of black hole feeding events. The bubbles reveal how often the black hole was active, how strong the jets were, and how the surrounding gas responded. Black holes not only shape space, but also shape time. The deeper an object moves into a gravitational well, the slower time passes for it. This effect influences the evolution of accretion disks and the appearance of events near the horizon. As time slows, near the horizon, events unfold at a different rate from the perspective of external observers. This leads to the peculiar observation that matter appears to linger near the horizon indefinitely, although in its own frame it continues inward. Time inside the horizon behaves in an even stranger way. Once an object crosses the horizon, moving toward the singularity becomes as irresistible as moving forward in time. No physical force can change this trajectory. Every path leads inward. The geometry of spacetime ensures this outcome. It reflects the fundamental principle that black holes define regions of no return. Despite extensive theoretical work, many mysteries remain. The internal structure of black holes is unknown. The ultimate fate of matter inside them is unknown. The exact nature of the singularity is unknown. The fate of information swallowed by black holes is debated. These questions reveal the limits of current physics. They show that black holes remain among the most enigmatic objects in the universe. As the universe continues its slow and graceful evolution, black holes remain among the most powerful and most mysterious forces in existence. They are reminders that cosmic life is built on cycles of creation and destruction. A brilliant star that once warmed its planets and illuminated its corner of the cosmos ultimately collapses into a silent depth from which not even light returns. Yet from this collapse, a new chapter begins. A black hole becomes a source of gravitational influence, shaping the space around it for billions of years. Every black hole born from a star carries within it the history of that star, the nuclear battles fought in its core, the collapse that forged its dense heart, the explosion that marked its final breath. All of these phases are recorded in the mass and structure of the black hole that follows. As it grows by feeding on dust gas and wandering stars, it continues to weave the story of its origins into the structure of the galaxy around it. In this way, a black hole is not a dead remnant, but a living force sculpting the universe long after its parent star has vanished. The largest black holes tell an even grander story. They are the memory keepers of galaxies. At the center of nearly every galaxy, a supermassive black hole sits in silent command. Around it, stars form and die. Clouds of gas spiral inward, heating to extreme temperatures as they fall. When a black hole feeds vigorously, its environment becomes one of the brightest scenes in the universe. A quasar shining with more power than millions of suns. When it rests, the galaxy builds itself peacefully around it. In either case, the black hole remains the gravitational anchor that holds the system together. The behavior of these cosmic giants offers deep insight into the past. Astronomers study their mass, their spin, and the structures around them to learn how galaxies grew. The earliest galaxies likely formed around the first black holes created not by stars, but by the high density of the newborn universe. These primeval black holes provided the seeds from which later cosmic structures emerged. Even now, each observation of a distant quasar or emerging pair of black holes adds a new piece to the puzzle of our universe's history. Modern science continues to uncover clues about black holes and the nature of reality. When two black holes collide, they send out gravitational waves that ripple across spacetime. Detecting these waves allows scientists to observe events that cannot be seen with light. This new way of listening to the universe reveals secrets about the lives of stars, the structure of spacetime, and the fundamental laws of physics. Every detection expands our understanding of the cosmos and places black holes at the center of modern astrophysics. Despite all that has been learned, countless questions remain. What happens inside the event horizon? Does the singularity truly exist? Is information lost forever, or is it preserved in some unknown form? Could black holes be gateways to other regions of the universe, or even other universes? These mysteries remain unsolved, and they challenge the limits of human imagination and scientific theory. Black holes push physics to its breaking point, forcing scientists to confront the deepest truths about the nature of existence. Yet even as black holes challenge us, they also inspire wonder. To imagine a star collapsing into an object so dense that time and space bend around it is to glimpse the extraordinary complexity of the cosmos. Black holes remind us how small we are, but they also reveal how far human thought can reach. From ancient observers who looked at the stars with curiosity to modern astronomers with telescopes and detectors, humanity has pursued the story of black holes across centuries. In this pursuit, one truth becomes clear. Black holes are not cosmic anomalies. They are essential parts of a universe's architecture. Without them, galaxies would not have formed as they did. Stars would not arrange themselves into grand spirals and glowing clusters. The universe, as we know, it would be vastly different. In their darkness, black holes bring structure to the cosmos, and their presence shapes the grand design of everything we see. As we look ahead, we know that black holes will continue to influence the future of the universe. Over trillions of years, stars will fade and galaxies will dim. But black holes will remain. They will wander through the cold darkness, pulling in stray matter and merging with one another. In the final ages of the cosmos, the universe may be filled mostly with black holes, silent and enduring. Eventually, Hawking radiation will cause even these ancient giants to evaporate, leaving nothing but faint whispers of energy floating in the void. In this distant future, the last traces of matter will vanish, and the universe will return to a quiet state. The story of black holes is ultimately the story of transformation. A star begins as a cloud of gas, then grows into a luminous sphere, then collapses into an object of pure gravity. Black holes demonstrate that endings are not true endings. They're transitions. They are gateways through which the universe reshapes itself. They show that the cosmos is not static, but alive, constantly evolving, constantly changing. In the end, black holes are not simply monsters. They are the sculptors of galaxies, the keepers of cosmic memory, and the most astonishing products of stellar life cycles. They stand as reminders that even in darkness there is purpose and power. From the ashes of dying stars emerge the engines that shape the universe. In this way, black holes are both the conclusion of one cosmic story and the beginning of countless others. This is how black holes are born, from stars to monsters, from light to shadow, and from creation to transformation. And as long as the universe exists, their story continues, drawing us deeper into the mysteries of space and the endless journey of understanding our place within it.